Hi everyone, this is Soumyadeep Paul, a mentor at CodeCurdos, and welcome to all of you on the day 5 of our DSA series. I hope you all went through the day 4 video and understood what time complexity is and how we can figure out and calculate time complexity in some generic codes. Now in today's class, in today's video, we'll be seeing how to calculate time complexity in a very famous algorithm called as merge sort. Okay, so let us understand. Now, if you don't know what merge sort is, don't worry. In today's class, in today's video, we won't be coding it. But I'll just explain how merge sort works. And then we will try to figure out the time complexity using something called as a recursion tree. Okay. Now see, in 99% of your interviews, your interviewer will not ask you how to derive the time complexity of merge sort. You just need to know that it is big of n log n. But as a good developer, it is your responsibility to know such basic things. Okay. Because the derivation of merge sort time complexity is a very basic thing and it will help you to visualize recursive trees in a much more easier manner. Okay. So first, let us understand what merge sort algorithm is. Merge sort algorithm. Okay. So suppose you have an array. Okay. You want to sort this whole array. What merge sort tells us is it is a recursive approach. It is a recursive algorithm. So I will divide my problem into two different halves. I will break my problem into two different halves. And I will ask recursion that, hey bro, please sort the left half. Then again, hey bro, please sort the right half. And recursion being a good friend of mine, I have complete blind faith on recursion that if I just call recursion on the left half, it will sort it and give me 136. Similarly, if I call recursion on the right half, it will sort the right half and give me 257. So once I call recursion on both the halves, my left half gets sorted, right half gets sorted. Then what I do is I divide them into two different smaller arrays. And then use a two-pointer method to again combine them back to the original array. Okay. So this is what the merge sort algorithm is. Now, if we look at from a recursive tree approach, it looks something like this. We have a tree, we have an array of size n. I am calling recursion. I am asking recursion to solve for n by 2 size array and n by 2 size array. Then for n by 2 again I will recursively ask recursion to solve for n by 4 array and n by 4 array. Here also n by 4 and n by 4. Okay. Then here for n by 8, n by 4 will be asking the function call where I pass an array of size n by 4. It will further make recursive calls on arrays of size n by 8, n by 8. Okay. And this will keep on going till I reach the base case. Now what will be the base case? This division will keep on happening till I reach the base case where I have just one size arrays, 1 or 0 size arrays. Okay. A lot of them. Okay. Something like this. 1 or 0 size arrays. When I have a 1 or 0 size array, I don't need to sort it any further because they're already sorted. So I can simply return. So this will be my base case in the entire recursion. Okay. Now my recursive tree approach of time complexity tells that for time complexity, what it tells that to find the time complexity, all you need to do is sum of number of nodes multiplied by input size for each level. Okay. So here number of node is 1, input size is n. So this will be 1 into n. Plus in the second level number of nodes is 2 and the input size is n by 2. So it will be 2 into n by 2. Plus in the third row, third level, number of nodes is 4 and the input size is n by 4. Plus here the number of nodes is 8 and the input size is n by 8. And this sum continues till this level, where say the number of nodes is, say, see here I have number of nodes is 2 power 0, here I have 2 power 1, here I have 2 power 2, here I have 2 power 3. So suppose this is the 0th level, this is the first level, second level, third level. Like this there are k levels. Okay, so let's say there are k levels. There are k levels. Okay, k plus 1 levels. Okay, so starting from 0th level, to first level, second, third, like that, the k plus 1th. So if there are total k plus 1 levels, starting from 0, the last level will be kth level. Okay. Then when I go from 0 to k, I'll have total k plus 1 levels. So here I'll have 2 power k nodes. Okay. So here I'll have 2 power k nodes into input size is 1. Okay, input size is 1. Now if you notice, in second level, I have 2 power 2 nodes. Okay. And input size is n by 2 power 2. Third level, I have number of nodes as 2 power 3 and input size is n by 2 power 3. So I can see a pattern. That at kth level, number of nodes is 2 power k and input size is how much? N by 2 power k. Understood? This is what I figure out from this pattern of looking at 0th level, first level, second level, third level, fourth level, and so on. So if somewhere down the line at kth level, if I am reaching 1, that means this is nothing but this will be what? This will be n by 2 power k, which approaches somewhat closer to 1. Okay, which approaches somewhat closer to 1. So that is why I can say that here last, instead of 1, I can also say n by 2 power k. Okay. So this becomes what? This 2, 2, 4, 4, 8, 8, 2 power k, everything gets cancelled. So this is n plus n. Here I can write 2 power 0 by 2 power 0. So I can say n plus n plus n plus n plus n plus till n. And how many n's will be there? 1 n for every level. 1 n for 0th level, first level, second level, third level, fourth level. There are k plus 1 levels. So 1 n for every level. And there are k plus 1 levels. So this becomes n into k plus 1. Okay. And what will be k? We said n by 2 power k is somewhat equal to 1. That means n by 2 power k is equal to 1. That means I'll take log on both ends. I'll say n is equal to 2 power k. I'll say log n is equal to k log 2. I'll send k is equal to log n by log 2 is equal to log n base 2. Okay, so this becomes n into log n base 2 plus 1. Now whenever we are talking about time complexity, n is usually pretty large. So there 1 can be ignored. So this becomes n into log n base 2. This is why we can say that the time complexity of merge sort algorithm is big of n log n. Okay, because this is the total work done, total work done. So my time complexity comes out to be big of n log n. Understood? Every node is doing some work, every recursive call is doing some work. Okay, so what is the basic gist behind this approach? The basic gist is every recursive call is doing some work. Every recursive call is doing some work. Okay. With this approach, we are adding the work of every recursive call. We are adding the work of every recursive call. Okay. So this is what is called the recursive tree approach. So I hope this is clear to all of you. Please visualize this a little bit. Just sit silently and think about it and you'll get it. Okay. So that's it for today's video. I'll see you all in the next video where we'll see how to use the same approach to find the time complexity of yet another famous algorithm. Okay. And if you want to learn these concepts in a much more in-depth manner, do join Code Cardos.